Hello, welcome to my channel. In this video, we are going to be solving problem under ideal gas. So we are given a problem of this form. So the question is, the equation of state of an ideal gas is given as PV equal to nRT, where N and R are constants. Our N here is the number of moles, our R here is the gas constant. So A, show that the volume expansivity B is equal to 1 all over temperature, which is capital letter T. B, show that the isothermal compressibility K, or known as Kepa, is equal to 1 all over capital letter P, which is pressure. To solve this problem, it's important for us to know the expression for the volume expansivity and the isothermal compressibility. And they are giving us this and this. Our volume expansivity is given by this expression where we have a change in volume divided by change in temperature multiplied by 1 all over the original volume at a constant pressure is equal to the volume expansivity. Likewise, a change in pressure which results to a change in volume, right, multiplied by 1 all over the original volume times minus 1 is equal to the isothermal compressibility. So, looking at this problem, you will notice that from our ideal gas equation, which is given as PV equal to nRT, we want to find an expression for dVdt from this expression. Now, if you notice, we have at constant pressure, so take note of this P. At constant pressure, we have dVdt. So what we want to find is a derivative of P with respect to V and T. So we have the P, because of this P, equal to the partial derivative of P divided by partial derivative of V times dV at constant temperature plus partial derivative of P divided by partial derivative of T at constant volume times dt. So from this expression, we notice that at constant pressure, our dP will be equal to 0. So we have this expression, and if we take this one to the other side, we have this expression. So at this point, we can pause here and go back to this expression. We want to find a connection between dP and dV from this expression. Now, from here, we can make our P the survey formula, and we get P equal to nRT all over V. If we find the P dV because of this expression, we can substitute our final result into this part. And we'll come back here again and find the P dt and substitute our final result into this part. Then we'll simplify from there. So let's find the P dV, and we have the P dV will give us minus nRT all over V squared. Remember, this V can go up here to become V raised to power minus 1. When you differentiate minus 1, it goes back to become minus. Then minus 1 will give us minus 2. That minus 2 comes down, we have this expression. So we can now have the P dV will be equal to minus nRT all over V squared. And that will be substituted here. So let's go and find the P dt. The P dt will just be nRV dt. I will substitute here. So we have this expression. And when we substitute, we have our expression for minus nRT for V squared over V squared. And this one, which is nR all over V, which is the P dt. And we have this expression. So what you notice is that nRV can take care of nRV, leaving T all over V. Minus we take care of minus, we have T all over V dV dt. Right? So we can make our dV dt the Soviet formula from our previous expression. We have dV dt, and our sending our V down to this point, which is equal to 1 all over T. And from this expression, right, we notice it's equal to our volume expansivity, and that shows that our beta, which is volume expansivity, is equal to 1 all over T. And that's what we're asked to prove. So we have finally that beta is equal to 1 over T. Okay, so let's go back to the next problem, which is, recall that our isothermal compressibility K is equal to this expression. Now take note of our T here, as usual. We look for the value of, we'll differentiate T with respect to V and P. So we have dt equal to partial derivative of T divided by partial derivative of P at constant V multiplied by dP. Likewise, this part too. So we now see at constant temperature, we have dt will be equal to 0. So we have 0 equal to this. So if we take this one to this other side, we have this equal to this. Now recall that our PV equal to nRT. But this time I want to find dt dP and dt dV. So we can make T the survey formula so that we have V. If we differentiate T with respect to P, we have dt, nR goes down, we have dP. dP will be differentiated, leaving V all over nR. If we also do the same thing for dt dV, we'll have dt P all over nR dV, so which is P all over nR dV equal to dt. Now that we know the value for dt dP and dt dV, we can substitute them into this expression. So we have V all over nR at constant volume dP equal to minus P all over nR at constant pressure dV. nR can take care of nR. And remember, since we are interested in dV dP, so dV dP comes down, V goes down, P goes down here. So we'll be having V all over P equal to minus dV dP at constant temperature. We now have 1 over P equal to minus 1 over V dV dP. Now, if you remember that this expression is nothing but our isothermal compressibility kappa. So that shows that our kappa is equal to 1 over P. And that's it. I hope this helps. Please like, share, and subscribe. Thank you.